So this problem says a cubic container of volume 2 liters. 2 liters is, hold your glass up please, twice that. That's a liter. Okay. So 2 liters hold 0.5 moles of nitrogen gas at 25 degrees Celsius. 0.5 moles meaning how many molecules there are? 1 mole is 6 times 10 to the 23, 10 to the 24. So 0.5 mole is 0.5 times 10 to the 24 molecules. Okay. This guy is 1 liter, so this guy is a quarter of a mole. So this thing has 0.25 times 10 to the 24 molecules. All right. What is the net force due to nitrogen on one wall of the container? And compare compare the force to the sample's weight. So this is a cubic container. Let's draw a cube. All right. The problem says what is the net force? Okay. So what we'll have to do is the following. See, here's atmospheric pressure acting from the outside, and then you have the pressure of the gas. Okay. Now, if this pressure is greater than this pressure, the force would be outwards. If this pressure is greater than that, it would crush the container. Okay. So we'll have to find the pressure of the nitrogen gas first, and then we'll calculate the net force. All right. First, let's find the dimension. L cube is 2 liters. So L is, by the way, a liter is 10 to the minus 3 meter cube. Okay, so L in meters is 2 times 10 minus 3 to the power 1/3 meters, and that is equal to okay, so the dimensions of the cube are 12 centimeters on the side. Okay? That's what we just found. All right, well, that will be used for later. Okay, so we have to find the pressure inside the container. Okay. So again, we will lean on nRT. They have given us N. They've given us the number of moles, so we'll use this form of the ideal gas law. The pressure is nRT divided by V. N is 0.5 moles. R is 8.314 joules per mole per Kelvin. Temperature is 25 degrees Celsius, 298 degree Kelvin. And volume is 2 liters, 10 minus 3 meter cube. All right, so this thing will work out too. Everything is in SI units, so the pressure will work out in pascals, and this 10 to the power 3 comes to the top and becomes 1,000. So all right, so let's do 500 times 8.314 into 298 divided by 236. Okay, so what works out is 6.19 into 10 to the power 5 Newton per meter square. That is the pressure. Okay, and this 10 to the power 5 Newton meters square is 1 atmosphere. So the pressure of the gas inside the container is 6.2 atmospheres, and you have 1 atmosphere acting in the other direction. Okay, so the net force, will calculate the net force. All right, so the net force will be, Okay, again, here's another diagram. Okay, and we want the net force on a wall. Okay, so the net force on one wall is P minus P naught times the area of the wall, which is L squared. Okay. All right, so P is 6.19 times 10 to the 5. P naught is 10 to the 5, and L is 0.126 meters squared. And this was Newton meter squared. So that works out to newtons. Okay, so this is 6.19 minus 1 is 6.19 minus 1 is 5.19. Okay, so 5.19 into 10 to the power 5 into 0.126 square newtons. And this works out to okay, so to the this works out to 824 newtons. Oh no, 2, 5, okay, 8, 2, this works out to 8.24 into 10 to the power 3 newtons, 8,240 newtons. Okay. Now this is your the weight. Most of you guys weigh about, let's say, 60 to 70 kg. We'll say 80 kgs. 80 times G is 800 newtons. So your mass is 800 newtons. So 8,000 newtons is 10 times your body weight. So the air inside this, if this were at 6 atmosphere, that nitrogen is pushing this wall. This is about with the force equal to 10 times your body weight. Okay, so that's what that is saying. All right, we'll say something more about it. Let's see, what does it say? Compare this force to the sample's weight. Okay, so let's calculate the sample's weight. Let me add a page below. All right, so half a mole, you have a half a mole of nitrogen, so N equal to, okay, nitrogen gas, okay, the weight of nitrogen gas is 28 atomic units. Okay, so 1 mole weighs 28 grams. Half a mole is 14 grams. And so the weight of your sample is 14 into 10 minus 3 kg times 9.8 meters per second squared. Okay, so here's why we calculated this. So the weight of the nitrogen in that is 0.14 newtons. Okay, so we'll calculate the net force divided by mg. Okay, and so 8,240 newtons divided by 0.137 newtons. $60,000, that's the ratio. What does this mean? So if you translate this, what this means is, if it were you can push with a force equal to 60,000 your body weight. That's what that is saying. So this is better than Superman. You fill that cup with with that nitrogen to a pressure of 6 atmospheres. You're getting a push 60 times its weight, 60,000 times its weight. All right. So if you don't have any questions, that takes care. Yep. All right.
You said that there's a pressure on the inside and the outside.
Right. The outside is
creating a force net. You're at your P dot or
P naught.
P naught. Where are you pulling that from?
That's atmospheric pressure.
That's just normal atmospheric.
Yeah. Okay. So right now the net force on this wall is 0 because the air inside is 1 atmosphere, the air outside is 1 atmosphere. The net wall on your chest is 0. The air inside your chest is at 1 atmosphere. The air outside is 1 atmosphere. This force is so great. If you go diving, you dive 33 meters, you have 2 atmosphere from outside. If you still had 1 atmosphere air inside, then your chest would get crushed. You have to breathe air at 2 atmospheres at 33 feet. Okay. When we get done with the problems, I'll show you a demonstration of the force exerted by air. Did we stop this? No.